Yes, hello students. Now we have finished the first part of Unit 1 where we discussed the dynamic torque equation and steady state stability. In the second part of this unit, we have to discuss how the motor rating is selected. What should be the rating of the motor for different types of loadings. So in this we shall discuss what is the thermal loading of motors. When the motor is connected to supply, it starts running and supplies some mechanical load. Some heat is generated inside the motor. That causes the motor temperature to rise. So how the temperature rises, on what factors it depends, and how we can select the rating of a motor for a particular application. So let us first discuss what is the thermal loading and what is the temperature rise when the motor is loaded. So suppose this is a motor which is connected to some supply. So you have given a supply here and it is supplying certain load. Some load is there. So what happens is that when we connect supply, because of that supply, flux is generated. That causes some iron loss in the motor. And when the load is connected and the motor draws current from supply, so windings gets heated because of copper losses. So these losses take place and that causes the motor to generate some heat. So here P is the heat generated per unit time, that is the power loss in the motor. So as the motor generates heat, its temperature starts rising and its temperature becomes more than the ambient temperature. So what happens is that as soon as the temperature of the motor rises above the ambient temperature, heat starts dissipating from motor to ambient. So you can say that the heat dissipation rate, that is heat dissipated per unit time, so it is given by D multiplied by the difference in motor temperature and ambient temperature. That we may call as temperature rise theta. So it depends on that temperature rise, and a constant D that we call as heat dissipation constant in joules per degree centigrade per second. So the heat dissipation depends on the temperature rise of the motor, that is the temperature of the motor above the ambient temperature. So what happens? There are different situations. The heat generated is greater than the heat dissipated. Earlier in the beginning, as soon as we start loading the motor, the temperature of the motor is small, but heat generated is high, heat dissipation is very low. So in the beginning, P will be less than PD. Sorry, in the beginning, P will be more than PD, that is heat generated will be more than the heat dissipated, and what will happen that the temperature of the motor will rise and the heating of the motor takes place. And suppose after you have run the motor for some time, motor has attained certain temperature rise and then you have disconnected the load. That is, the power loss is reduced. Then what will happen? That heat dissipation is higher, but the motor is generating less heat now. So P will be less than PD. In this case, the temperature of the motor will start decreasing. Heat dissipation is high, heat generated is less, so the temperature of the motor will decrease, and you can say that cooling of the motor takes place. And what happens in steady state, when you have loaded the motor and gradually the heat is developed and the heat dissipated increases, this heat generated is constant. One stage will come when heat produced is equal to heat dissipated, and thereafter the temperature of the motor will become constant. The total heat generated is equal to total heat dissipated, and this you can say the stability is reached, and that temperature we call as steady state temperature rise, theta m. So let us find out what is the expression of the steady state temperature rise. Now let us say that heat generated in time interval dt. Let us take a small time interval dt. So in this case, the heat generated in time dt will be equal to power loss multiplied by dt. So power loss in joules per second. So this will be in joules. Similarly, heat dissipated will be equal to Pd, rate of heat dissipation, multiplied by the time dt. If you put the value in terms of d and theta, Hd will be equal to d theta into dt. So this is our equation number 2. Now what is the heat absorbed by the machine? Heat absorbed can be written as your familiar equation ms theta. You might have studied in your 10th or 11th classes, that heat absorbed by any material, any object, is mass multiplied by specific heat multiplied by change in temperature during the time. So here Ha is equal to m, mass of the motor, S is the specific heat of the motor material in joules per kg per degree centigrade, and this d theta is the temperature rise. So you can write as Ha is equal to C into d theta. C is another constant, which is mass multiplied by specific heat, and this is nothing but the thermal capacity of the motor. So Ha is equal to C into d theta, our equation number 3. Now what is the heat absorbed? It can also be written as heat generated minus heat dissipated. Heat is generated and some part of the heat is dissipated, remaining heat is absorbed in the motor. So heat absorbed can be written as Hg minus Hd, our equation number 4. Now you put the values of Ha, Hg and Hd from the previous equations. So it is C d theta is equal to P dt minus d theta into dt. Write it in a slightly different way. You take on this side. So P is equal to d theta plus C d theta over dt. So this is equation number 5. This equation is similar to the equation that we already know in series RL circuit. V equal to Ri plus L di over dt. Similar equation is there, and you will get similar solution. Now let us try to solve it. So in such situations, the solution will have two components. One is the steady state term, other is transient term. The steady state term is P upon D. In case of electrical circuit, it was V upon R. So it is P upon D plus some constant into e to the power minus T upon C by D. C by D, earlier it was to the power L by R, that we called electrical time constant. So here it is C upon D. Let me give it some name. It is TH, tau H. Tau H is known as heating time constant of the motor. And theta SS is steady state temperature rise. That is when the motor is loaded for large time, for enough time, the temperature will rise and gradually and finally it will reach certain temperature rise. When P equal to PD, that temperature rise is theta SS. Now this is the third type of time constant that we have studied in this course. Earlier we studied the electrical time constant, that was in the range of some milliseconds. Then we studied the mechanical time constant, how the motor gains speed, and that was in some tens of seconds, maybe around 1 minute. And this heating time constant is much higher than even mechanical time constant. So its range may be in some tens of minutes. 20 minutes, 30 minutes, 40 minutes, even 1 hour. So motor takes time to heat up. When the motor is loaded, the temperature rises gradually and it may reach the steady state temperature rise in about 1 hour. So this is the third type of time constant, that is the thermal time constant of the motor, or you may call as heating time constant of the motor. When cooling takes place, we have another time constant that we may call as cooling time constant. So this is the solution where k is some unknown constant. Its value can be determined by knowing the boundary condition. That is, if at t equal to 0, when at the starting the temperature was theta equal to theta 1, it may be possible that the motor is started earlier, supply is connected, and after some time the load is connected. So when the motor is started, it is not loaded, copper losses are negligible, only iron losses take place, and because of the iron losses, the temperature of the motor will rise and it reaches the steady state value of say theta 1, and then we have put the load on the motor. So in that case, at t equal to 0, theta will be equal to theta 1. You must remember that theta is the temperature rise. It is not the actual temperature of the motor. It is the temperature of the motor above the ambient temperature that you can see from here. Theta is theta m minus theta a. Motor temperature minus the ambient temperature. So at t equal to 0, theta equal to theta 1, you put the value here. So theta 1 is equal to theta ss plus k into 1. This means that k is equal to theta 1 minus theta ss, our equation number 7. Now you put the value of k from 7 in equation 6. So theta equal to theta ss plus theta 1 minus theta ss e to the power minus t upon tau h. This again you can rearrange, and theta will be equal to theta ss 1 minus e to the power minus t upon tau h plus theta 1 e to the power minus t upon tau h, the final equation for temperature rise, equation number 8. Now if t equal to 0, if theta 1 is equal to 0, that is we have started the motor when the motor was at the ambient temperature, and we have started the motor and put the load on the motor immediately. In that case, theta 1 will be equal to 0, that is initial temperature rise is 0, or the motor temperature was equal to ambient temperature. In that case, theta 1 will be 0, and you will get the equation theta equal to theta ss 1 minus e to the power minus t upon tau h. So if you plot it with time, it will somewhat like this. It will gradually rise to reach the steady state temperature rise. This time in which the temperature becomes equal to theta ss may be in the range of say 40 or 60 minutes like this. It is not in seconds, it is in some minutes, 40 to 60 minutes you may call it. And when the initial temperature rise was 0, then this will be the curve for steady state, for the temperature rise of the motor. Now what is the effect of time constant? If time constant is higher, motor will take longer time to reach the steady state. If time constant is less, it will take shorter time to reach the steady state. So this curve shows the different temperature rise of the machine for different values of time constant, and time constant depends of course on these two constant of the motor. So for one particular motor, this will be a constant. So this is what happens during the heating of the motor. Now what happens when the load is disconnected? The motor will cool down to ambient temperature. So what happens during this we shall discuss just now. Now what happens during cooling? What you can do, you can either switch off the supply, load is disconnected, motor stops, and of course when the motor is stopped, no heat is generated, and the motor will continue to dissipate the heat to the atmosphere. Its temperature will go down, and finally in steady state the motor's temperature will become equal to ambient temperature. In the second situation, this may happen that we have just removed the load or reduced the load such that losses are taking place, but it is less than the earlier losses. In that case, the motor's heat generated will become less. Heat dissipation is high. The motor will cool down, and it will settle to a new value of steady state temperature rise. So let us take this general case when the motor is not disconnected, rather it is you can say the load is removed or the load is reduced. So in this case, let us say that in this new situation, the power loss in the machine is P dash, which is less than the earlier power loss, that is equal to P. So write the similar equations and you will get this equation: P dash is equal to D dash theta plus C d theta over dt, where D dash is the new value of heat dissipation constant. So solution of this will again be of the same type: theta equal to P dash upon D dash, that is the steady state temperature rise, plus K dash new constant e to the power minus T upon C upon D dash. This C upon D dash you may call as T tau C, that is the cooling time constant. You may call it as cooling time constant. Sometimes cooling time constant may be different from heating time constant. Sometimes it may be same. So this is the case now. Now you have to find out the constant K dash from the initial condition. So let us take that at T equal to 0, the temperature was theta 2. Because of previous loading of the motor, temperature reached a certain value, theta 2. So that is the initial temperature rise of the machine. So if you put that, you will get K dash equal to theta minus theta SS dash. You put the value here and you will get the final solution as theta equal to theta SS dash 1 minus e to the power minus tau upon tau C plus theta 2 e to the power minus T upon tau C. Now if theta 2 is equal to, if theta SS dash is equal to 0, and this will happen when the motor is disconnected from supply, that is power loss is equal to 0, or you can say that P dash is equal to 0. In that case, theta SS dash will be equal to 0, and the equation simplifies to this form: theta equal to theta 2 e to the power minus T upon tau C. So you can plot these two curves. In the first case, when the motor is not disconnected, initial temperature rise was theta 2, and that may come from the previous loading of the motor, and you have reduced the load at this instant of time. Either you have removed the load but the motor is connected to the supply. So in that case, the motor will cool down and it will reach the new value of steady state temperature rise, theta SS dash, that is proportional to P dash, that is losses taking place during low load or no load period. On the other hand, if the load is removed and the motor is switched off, in that case the motor will cool down to 0 temperature rise during steady state condition. So these are the two cases as per the two equations that we have arrived earlier. So in that way the motor cools down to a new value of temperature rise. So this is the heating and cooling of the motor. So how the motor behaves thermally? Now the motor is designed for certain temperature rise or for certain temperature. The motor's winding, the motor's insulation, they are designed for certain temperature. Suppose the motor is designed for 100 degrees centigrade. So this means that motor can be safely loaded till the motor's temperature becomes equal to 100 degrees centigrade. So if the motor is overloaded and temperature becomes more than that value, the motor will get damaged. So you have to know how to load the motor so that the motor reaches its designed value of steady state temperature rise. So we have to select the motor of proper rating. For example, if you have some certain situation where the load is coming only for short interval of time, the temperature hitting time constant is say 60 minutes. So this means that if the motor is loaded continuously for 60 minutes, then it will reach its steady state temperature rise, and for that the motor is designed. But if the load is coming only for short interval of time, then you can overload the motor. You connected a higher load on the motor, and during the short interval of time, the temperature rise may become equal to the permissible value of temperature rise. So how to choose the motor rating for different situations, for continuous loading, for short time loading, or for intermittent loading, we shall discuss in the next lecture. Thank you for today.